Auditory Analytics is a methodological framework that includes data sonification and analytical listening as an integral part of an iterative cycle of data analysis for scientific insight and discovery. Data sonification is not an isolated goal in itself. It's part of a larger cycle that includes collecting raw data, deriving data sets, designing multiple mappings of data to sound and to visual representations, analytical listening, forming hypotheses, and building tools. It's typical to go around this loop many times, generating multiple different mappings, building new sonification tools, and often collecting additional raw data before going around the loop again. A lot of attention is paid to techniques for mapping data to sound and to sound synthesis and processing models. But the dual of data sonification, analytical listening, is equally important to auditory analytics. The ubiquity of meaningless sound in daily life is training us to receive sound in a passive way, allowing it to wash over us without interpretation or to quickly relegate it to the background. Analytical listening is different. It's not just hearing, it's actively listening to an audio signal with the expectation that it carries meaningful information. Each of us has the innate capacity to interpret sounds in the natural world. Analytical listening taps into that ability, allowing us to extract information encoded into a synthetic sound. Mathematician Richard W. Hamming wrote, "The purpose of computing is insight, not numbers." In auditory analytics, the purpose of sonification is not sound, but insight. Each sonification acts as a catalyst, sparking new hypotheses and guiding research in unanticipated directions. For example, Martin Krubela's lab at the University of Illinois used auditory analytics to study the patterns of hydrogen bond formation during the transitions of a small protein between its folded and unfolded states. When in its unfolded state, most of a protein molecule's hydrogen bonds form with the surrounding water. But some amino acids are hydrophobic. They act like oil and are repelled by water. This causes the protein to fold in on itself with all its oily sections hidden in the center. The collapse allows the rest of the protein to form a stable network of hydrogen bonds directly with itself, creating a compact structure. For this study, we focused on the sequence of events during the transition between the folded and unfolded states. Over the course of the study, we traversed the auditory analytics cycle multiple times, listening to many sonifications and looking at many visualizations in a cycle of analysis, hypothesis formulation, reanalysis, and remapping. Eventually, this led to the idea that the hydrogen bonding patterns might be associated with different pathways through the state space. So we made an animation of the center region of the protein while it folds. Hydrogen bonds are shown here as dashed lines. As you watch the animation, see if you can spot any patterns in how these bonds form and break. We found it nearly impossible to track this number of spatially separated events with our eyes. There are multiple bonds scattered across the visual field, and the molecule is rotating, so key bonds are often hidden from view, making it incredibly difficult to detect when bonds might be changing together. But this is exactly the kind of task where the auditory system excels. The auditory system evolved, in part, to help us track multiple sound sources in a 360-degree environment, even in partial or total darkness. We're especially good at this when the sounds are separated in time and location and occupy different frequency bands. So we tried mapping each bond event to a sonic event, a grain of sound, where each grain is localized in time, in pitch space, and in stereo position. Now we get to the analytical listening stage of the cycle. The thing about analytical listening is, 1, you already have an innate ability to do it, and 2, everyone gets better at it with practice. For example, listen to the direct H-bonds forming between different parts of the protein with itself, and take note of when you hear a dramatic change in the soundscape. You've just used your ears to identify one of the signature patterns of hydrogen bonds associated with a transition to the folded state. By listening to subsets of amino acids and H-bond types, we immediately heard an association between dynamic H-bond formation patterns and how quickly or slowly a transition occurred. Then we spent a lot more time confirming what we'd heard by automating the identification algorithm and performing standard statistical analyses. Our ears told us there was something to find. We just confirmed it with modeling and statistics. Coming full circle, in the process of reverse engineering how we identified the H-bond patterns by ear, we also came up with a new visualization tool, the piano roll. The piano roll, used in conjunction with the H-bond sonification, makes it easier to detect cooperativity among spatially separated H-bonds as they form or break during the transition. The parable of the blindfolded scientists and the elephant is a reminder that no single data set, visualization, or sonification can ever provide a complete map of a phenomenon. Instead, scientific facts are established progressively through a cascade of evidence. Experiments, building models, running simulations, making observations, gathering raw data, extracting derivative data sets, mapping those data in multiple ways, sonifications, visualizations that are analyzed to build new models and verbal descriptions, each stage of which contributes to transforming raw data into a cohesive, cumulative argument. In auditory analytics, data sonification and analytical listening form an indispensable part of that cascade of evidence.